So first of all, thank you for the invitation and organizing the webinar. Thanks to the Wasser Agenda and 20, and thank you all the participants. I see that there is a great interest in the topic, as Simon already said. So I'm really glad about it. And I wanted also to thank the people who responded to the questionnaire that we post on the webinar information. So I will use the results of this questionnaire during my talk and also during the discussion afterwards. So although all of you or most of you already know because you registered to this webinar for a reason, it is important to start by defining what I mean by in-stream wood. And by in-stream wood or wood, I just refer to natural trees falling into a river. So when a tree falls in a river, becomes in-stream wood, usually with size larger than 1 meter and 10 centimeters in diameter, which is not very relevant. And here, when we study wood in rivers, there are two different ways to see this topic. On one hand, what happens to a river when a tree falls, and on the other hand, what happens to the tree when it falls into the river. And my research has focused mostly on the second question, so wood dynamics, but I'm covering the two aspects during the talk. So this is the structure of this talk. I will divided in three parts. So the first part is just about the effects, the functions of wood in rivers. The second part is more about wood dynamics and what happens to the tree once it entered the river. And finally, I will discuss or briefly show the challenges managing wood in rivers, so the wood-related hazards, different management strategies, and remaining challenges. So let's start by the first question, what happens to the rivers? So before I start describing the effects of wood in rivers, I was also positively surprised by the responses to the first question of the questionnaire. So we ask you to picture a river and whether it had wood in it or not. And most of you those who responded, and by the time I prepared this presentation, it was 84 people, but I know that more people responded afterwards, so we will update the responses. But then in any case, most of you picture, imagine rivers with wood. And also it was interesting to see that most of you agreed on the statement that rivers with wood are more natural than rivers without wood. And I was surprised because when you search for river in the internet, all the pictures that appear, or most of them, they completely lack wood. So wood is absolutely absent from the general picture of rivers. And the same happens if you search for mountain rivers. And nowadays we need to ask also the artificial intelligence. And so again, if you ask for designing a picture of a river, it's really hard to get images of rivers with wood. So you really need to be very specific on what would you mean by a river with wood. And by default, rivers do not have any wood. So that's interesting because this seems to be different from also the responses in other countries. So I will go back to this later. So some of the concepts about wood in rivers relate to the types of wood. And so the first distinction we need to do is between naturally occurring wood, so natural wood falling into the river, compared to artificially introduced wood. And during this talk, I will refer mostly to natural wood, but I will also mention and show you some aspects of artificial wood. So Wood is typically the largest wet material entering into rivers, so it's usually larger than the sediment, the coarse sediment, even boulders, and especially if the wood accumulates into jams. And in addition to that, wood is an important element because it's the base of the organic matter pyramid in aquatic ecosystems. And it's also a very important reservoir of organic carbon. So together with the living trees, wood stores organic carbon. And this is the foundation of the food web in river ecosystems. Wood provides multiple functions and services across temporal and spatial scales. So the local effects at the in-channel scale drive river reach pattern changes, and these changes influence river processes at the catchment scale. So wood influences the river hydrology, geomorphology, and ecology. We need also to distinguish, or the effect of the wood depends also on the size or the type of wood. So here we can distinguish between single wood pieces, single elements, and wood jams or wood accumulations. And also whether these accumulations are spanning the whole channel or they are accumulating on one side. So channel spanning versus non-spanning wood accumulations. And we need also to distinguish between stationary wood and mobile wood. And this depends on the time that the wood remains stable in the river. And most of the research on wood has focused only or mostly on stationary wood. And it's only recently that the benefits of mobile wood have been described. And I will go back to this also later. So now let's see what are the effects of wood in rivers. So the first type of effects are effects on the hydraulics. So the wood forms an obstacle, and this obstacle creates an obstruction to the flow that alters the local hydraulic conditions, modifying the streamlines and increasing turbulence. In general, wood reduces flow velocity, as you see in this graph, where we have flow velocity for different discharges and points are river reaches. And so here they compared in this river from Spain, reaches with wood versus reaches without wood. And usually the reaches with wood showed lower velocities. And the obstruction to the flow also creates a backwater effect. So spanning wood creates steps in mountain rivers, and these steps might be and are very often higher than boulder steps. And so from this data from Chile, we can see in this graph the height of the steps, and the height was much higher in those steps formed by wood. And these steps modify the longitudinal profile and the slope of the river. So the standard deviation or the variability of this longitudinal profile is also larger. But not only steps, wood also creates pools. And in this example from Spain, where they reintroduced wood, they observed an increase in the number of pools and also in the variety of these pools after just a couple of years from the reintroduction. And the reduction in the flow velocity results in a reduction also of the flow transport capacity. So this causes the deposition of sediment. And so there is a positive relationship between the amount of wood in a river and the volume of sediment. So the more wood, the more sediment the river is able to store. And not only the amount of sediment that is retained because of the wood, but also the grain size is affected by the presence of wood. So the wood accumulations retain finer sediment, which is shown in this graph, finer sediment that otherwise would be washed away. So fining the sediment grain size. Although wood may protect from bank erosion, usually spanning wood jams can also enhance channel widening. And this is because the accumulation of sediment causes aggradation or the vertical increase in the channel bed, and this causes lateral erosion or channel widening. And as you can see in this graph, where we have channel width versus the distance along the river, these peaks where channel width is much wider correspond to places where there are wood jams. So these local changes at the river scale, they may affect the morphology of the river. And in this graph, they show that after the reintroduction of wood, the morphology of the river changed from single thread to almost a braided system or a multi-thread channel. Wood also provides a hard substrate for the biofilm to colonize, and the biofilm is very important because it's the base of the food web. But also because of the fine sediment, this enhances or improves the conditions for the sheets and provide moisture for the growth of plants. And wood accumulations and the trapped sediment may force the establishment and development of vegetation and accelerates the process of island formation and evolution. And it's not only because of the sediment and the conditions, the moisture, it's also because some species, like poplar, they may resprout even after being eroded and transported long distances. So the interaction between flow, sediment, and wood produces in general better conditions for many species, macroinvertebrate and fishes, and enhances the habitat diversity and suitability. The presence of wood also influences the water chemistry and temperature. And the wood might be used by many species and not only aquatic, as you can see in the pictures here. So the species can be attached and might be dispersed by the wood and survive during a flood. And I will go back to this also later. Wood supplies food, shelter, and spawning areas for fish and other species. And in summary, wood influences the entire food web, improving the river's biological and ecological diversity. And this knowledge is now well established, and not only among the river scientists, but also among practitioners and regulators, as this was nicely shown by the respondents to the questionnaire. So wood is essential to sustaining and restoring river biodiversity. Still, wood is very often removed from rivers, so it is important to remind what happens when we remove wood from rivers. So by removing wood, we increase flow velocity and transport capacity, we decrease sediment and organic matter deposition, we enhance channel incision and erosion, simplify and homogenize morphology, we lower habitat suitability, availability, and diversity. So we lower biodiversity and ecological integrity, in the end, lowering resilience. So this is why wood that has been historically removed from rivers is now very often reintroduced worldwide, not only in Switzerland, for river restoration. And most of the projects report positive and successful results. As you see in this graph from a review already done a few years ago. And those projects which did not report positive results usually were related to planning and design problems, the type of wood that was used, or where and how the wood was installed. So what type of wood is used in restoration? Here we need to distinguish between artificial fixed anchored wood structures, and among them between simple deflector-like structures to more complex engineer log jams versus mobile natural-like wood with limited anchoring. And while in principle using non-fixed natural-like wood structures may result in more natural channel features, and this would actually result in a more sustainable river management, because they mimic better the natural wood in rivers. Usually anchored structures are used, and this is because the major concern when using wood in rivers is stability and structure failure. However, the few studies that looked and quantified the structure stability have reported very low structural failure rates. So in this example, that comes from the US, they quantified failure or characterized failure as the structure moving from its original location and losing its function. And from the graph, you can see that the reported failure rates were generally very low, with a mean and average value below 30%, and only few of them reported very high failure percentage of failure rates. And the other example, a more recent example from Australia, where they reported failure rates over time, they also observed relatively low, so moderate or major failures for very small percentage of the structures being monitored. Even after 10 to 15 years, the percentage was still below 30%. And they also quantified the decay of the structures, and again, most of them presented very low decay. But studies like these are very rare, so monitoring the structures after the installation and reporting failures is really important to assess and quantify these failures. In any case, wood is not supposed to be stable in rivers. Wood moves, and having mobile wood is also very important as it provides additional benefits. For example, provides a mechanism of dispersion and refugia, as you could see in the video. I go back. Yeah, here. So this is an example from a log right after a flood in the Spol River in Graubünden, and you could see many small animals moving. So these organisms survived the flood because they were attached to the wood, and they were also dispersed and transported with it. So mobile wood provides additional benefits like the uh, dispersal on refugia, but also dissipates flow energy, and the transported wood replenish the large wood downstream, and also the motion of wood creates more diversified wood in the river and allows for wood continuity, which is a topic that still remains to be defined and explored. So the next part of the talk is about mobile wood and wood dynamics. And to define wood dynamics, we recently defined the natural wood regime in a similar way than the flow and sediment regime have been defined. So together, the three regimes regulate the river's physical and ecological functions. And like the flow and sediment regimes, the wood regime consists of wood supply, transport, and storage, and they can be characterized in terms of frequency, magnitude, timing, but unlike the flow and sediment regime, much less is known about the natural wood regime. and only few sites have been monitored, and the wood regime has been quantified partially, and most of the cases only single aspects of the wood regime are explored. So the first part of the wood regime relates to the wood supply, and this video shows an example how wood is supplied to rivers by processes like landslides, but also bank erosion or fluvial transport from upstream. And so in principle, if you identify these areas affected by these processes and the forest density, you could easily estimate how much wood could arrive to a given point or any river. But wood supply is not stationary, it changes through time. And so in the framework of the wood regime, it could be defined according to the magnitude, the frequency, and the duration, which in the end all depend on the mode of recruitment or the recruitment processes. So identifying the dominant recruitment process is a key for management. And one unique example that examined this aspect comes from after the floods in 2005 in Switzerland, when large quantities of wood were mobilized, creating additional damages, as some of you may remember, or you can see on these images from Bern. And so the VSL made a survey afterwards and identified the most relevant processes supplying wood to the rivers. And they quantified how much wood was supplied by these processes. And this is what is shown in this graph. So here you have the wood supplied for different processes and also the wood that was in the river. And this is the first interesting observation here, that the presence or the wood in the river was very small compared to the wood supplied during the event by other processes. And among the different processes, bank erosion was the most relevant one, especially in larger catchments. And this is what we wanted also to explore in this other study, where we applied a GIS model to 40 catchments in Switzerland. And here in this graph, you see the results in terms of the contributions or the percentage of wood volume of each process. So we considered landslides, debris flows, and bank erosion. And in orange, we estimated the amount of wood in the river. So again, you see that this is a very small percentage. And for a frequent scenario of low magnitude events, you see the green color is dominant in this graph, meaning that the most relevant process is bank erosion, especially in large catchments. So here you have a set of catchments from very small ones to large rivers. And in a rare scenario or higher magnitude scenario, the importance of landslides and debris flow change, especially in small catchments, but still in the larger rivers, bank erosion is the dominant process. So these, of course, were model results. And when we compared these two observations, we saw that there was a large discrepancy, or the largest errors in this graph, they are represented by the size of the marker, where for the larger catchments. And this is because the model computes all the areas prone to these processes, to landslides, debris flow, and bank erosion, while during an event, only part of the catchment will be active or affected and contributing with wood. So that's the key challenge here, to identify which parts of the catchment, which torrents, which parts of the river will be affected by these processes. So the second element of the wood regime is the wood storage or load, which is usually computed in terms of volume per surface, per area, or per uh, longitudinal distance. And again, it can be defined in terms of magnitude, frequency, and duration, because again, storage is not constant, it changes through time. And this graph shows you a theoretical example of a river which um, shows a significant increase in wood storage after a debris flow, and then the wood storage decreases through time because of the transport during low flood magnitude events. But wood storage also changes in space, not only in time. And the mode the wood is stored also changes according to the river or the river morphology. So we usually have more dispersed, scattered wood accumulations on braided multi-thread channels, while we have more aggregated wood accumulations, so wood jams towards meandering rivers. And there might be also different types of accumulations that have been classified by some researchers. So in meandering rivers, we have jam accumulations usually on the concave banks and the point bars. But where the wood is stored, it's also changing depending on the discharge. So in this study, we computed the positional probabilities using numerical modeling for different flood scenarios. And you see that the areas more prone to accumulate wood changes from the different scenarios. And what we observed is that for during extreme flood scenarios, the floodplain is the natural depositional zone. And what happens nowadays is that the disconnection between the river and the floodplains limits the deposition of wood and enhances its transfer downstream. So not only where, but also how much wood is stored in rivers. A few years ago, we reviewed the existing data, and this graph summarizes the wood storage for different rivers in different countries. And what we see is that the scatter is very large, so there is a high variability, with some rivers showing a very large quantities of wood, like for example this case in Canada. And by the time we did this review, we had only a few streams from Switzerland, and as you can see, the amount of wood actually was comparable to the amount of wood in other rivers. So we wanted to update this data, and we compiled data from other rivers, also expanding a bit the type of rivers, because this first data set here illustrated or shown by the blue dots, they were generally very small rivers. So here we have wood load versus a drainage area. And then we expanded to look into wood storage in larger rivers. And what we saw is that the points lie on the lower part of the graph. But in all cases, we remain in the mountain area. So here you have again wood load versus elevation. And then we compare with this global database that we reviewed a few years ago. So this agrees with the general perception shown also by the questionnaire that rivers in Switzerland or in general, but in Switzerland as well, they have reduced quantities of wood. So what are the drivers controlling the storage of wood in rivers? The first one is the type of trees, so no wood without trees, but also the different species, have an influence. So rivers crossing coniferous forest usually have more wood than rivers crossing deciduous or broadleaf tree forest. Um, and usually the wood is also higher, the wood load or wood storage, as the forest age increases. So rivers and streams in young and managed forest or crossing young and managed forests usually have significantly lower amounts of wood, as also shown in this other graph. But the amount of wood varies also along the longitudinal profile of rivers and as the river size increases. In general, what we see is that the wood load has a negative trend compared to river width. So the wider the channel, the lower the amount of wood in it. And so we can explain this by the fact that small streams in the headwaters might be transport limited, while larger rivers in the lowland might be supply limited. So here, this part of the river network, the rivers have a higher transport capacity, but they may receive less amount of wood. However, we need to consider that the trend or the influence of humans and the human pressure also increases in the same direction. So we cannot disentangle the trend from the management. But in general, wood also remains longer in rivers crossing conifer forest compared to, again, deciduous or broadleaf trees. And this is because of the decay, so the wood decomposition, which is slower in the case of the conifers and is faster in the case of the broadleaf trees. And the decay or the residence time, the time that the wood is in the river depends on many factors, not only the species, but also the wood characteristics, the flow regime, etc. The next element of the wood regime is the wood transport. So like sediment, wood is mobilized in rivers during floods. And again, this is changing through time and transport is highly variable. But the main challenge here is the lack of observations compared to sediment, for example. So here there are only a few rivers that are being monitored worldwide. So how does wood move? Usually floating. So as you see in this video from the Lawi River, um, during floods, large quantities of wood might be transported, but not always floating. So in some rivers, wood may also form these fronts that are more like a debris flow process. But the important question here is how much uh, can be mobilized during a flood. And this is a video that I always show from the Sulk River because this is a very interesting river. So in this review that we did a few years ago, we compiled the volume of wood exported, transported during a flood versus the catchment area here. And what we see is that the conditions or for the same river, the amount of wood that can be transported during a flood is really variable. And this is exactly what we see in the Sulk River, where this type of uh, wood-laden floods are quite frequent. So here what is important is the flood history, but most important is the wood availability. So how much wood is in the river uh, when the flood arrives. But how much wood is moving in terms of the in-stream wood. So as I said, there are only a few sites where wood is being monitored. And in this graph, you see the data from these sites where wood is actually tracked and tagged and followed before and after floods. And some of these rivers have been monitored for years. So here you see the proportion, so the percentage of wood pieces moving for the entire survey period, survey time. And what we see is that the percentage of mobile wood is relatively low. So in most of the cases is below 20%. Only this case, this river in the UK showed a relatively larger mobility, but also note the number of pieces that have been tracked. And also they were tracked during a very short time. While if you see in the other cases, thousands of pieces and observations have been compiled. So yes, wood moves, but maybe not that often and also not that much. So what are the factors controlling wood mobility? The first one is the size of the wood. And here there is a very good proxy to estimate the likelihood of movement. So the length of the wood related to the channel width, but also the diameter related to the water depth, as this would control buoyancy. So in general, larger rivers, they show higher wood mobility, while small streams, they are characterized by lower mobility. And then how the size of the wood is changing through time is also important because this has an effect on the transport. And so there are, again, very few studies which looked at this topic. So the first thing is how different the size of the wood is once the wood arrives to the river. So after the flood in 2005, in a study from different catchments in Switzerland, they compared the size of the wood in the rivers versus the living trees, um, taking data from the forest inventory. And what they observed is that trees in the channel, so the wood in the channel, reduced on average 20% the original tree height. And then once the wood is in the river, the first thing that happens is the reduction in the branching complexity, or the trees, the first thing they lose are the branches. And this happens quite fast. So in this study in France, they observed that most of the branches are lost within 2 years, even without transport. So the pieces remain stable, but the branches are still being fragmented. And once in the river, the fragmentation, so the changes in the length, also happen very slowly. So in this site in Chile, or in these two sites in Chile, we observed that most of the pieces reduce their length less than 30%, and only a few of them really reduced significantly their size after more than 7 years. And that's important because smaller pieces are entrained more easily and travel longer distances. Unlike the branches that are lost very fast, the roots are not lost so fast. So they remain attached to the wood for longer times. And this also influences transport. So we have observed in many rivers that wood with roots move less than wood without roots. This is what is shown in this graph. But what's interesting here, and this is an example from Chile, but we have seen the same in many Swiss rivers is that the proportion of wood with roots is very low compared to the total amount of wood in a river. And that's interesting because in many restoration projects, the most frequent element of wood are roots. Um, so another aspect to consider is the density of the wood because this controls buoyancy and then affects transport. And again, the wood in a river usually shows a smaller density or lighter density than living trees. And also because of the decay or decomposition processes, biochemical processes, the density is reduced through time. And this again has an effect on the transport. So the lighter the density, or if we see it the other way, the higher the density, the smaller the transport, or the lower the transport or the mobility. But not only the wood, also the river controls mobility. So the morphology is very important. And this is what we saw in this study where we compared applying numerical modeling, but also compared to observations, two different river reaches. One channelized a straight, relatively narrow channel versus a very wide, natural, braided river reach. And so in this graph, you see transport ratio. So this is the percentage of wood pieces being transported through these reaches. So the first observation is that straight channelized reaches, they transport, they have larger or higher transport ratios. But also the transport competence or the size of the wood that is the flow is able to transport in this channelized system is much larger. So by channelizing rivers, we increase the transport capacity and competence. So we can move more wood and we artificially increase the transport of wood. While braided systems like this, they are the natural retention zones of rivers. And then the next question is how far the wood is traveling. And so again, from the few studies where they monitor wood, here we compile the observed transport distances. And what you see is that wood is usually traveling shorter distances. So traveling distances longer than 1 kilometer has a very low probability. And when the wood moves during a flood is also very relevant for management. So this example shows you two floods, two consecutive floods in the Sproul River. And here in blue, you have the hydrograph. And in violet, you have the wood fluxes. So many interesting things we can see here. But the first one is that the peak of the wood flux or the wood transport happens before or during the peak of the flood, and then during the uh, falling limb, wood transport is um, very low. And then another interesting thing is that the second flood showed much lower wood transport, even though the discharge was much larger. And this is because there was no supply in between. So most of the wood that was in the river was already transported during the first flood. And so this also illustrates that wood fluxes are not only governed by the forces of the water, but the availability of wood, the flood history, and also the river morphology are important. So we entered the last part of the presentation about the challenges managing wood in rivers. So the main challenge are the potential hazards. So the transported wood may accumulate critical sections like bridges, like this case, for example, in New Zealand. And this, of course, increases the impacts of flooding. So this is the same for bridges, but also dams and other infrastructures. But what is important to stress here is that um, those dangers or those hazards related to the transport of wood are not posed by the wood itself, but they are the consequence of the obstacles and infrastructures that were not designed to allow the wood to pass. And this is a legacy effect on wood in rivers because we artificially increase the trapping efficiency of rivers. So on one hand, we artificially increase the transport capacity. On the other hand, we artificially increase the trapping efficiency. Still, images like this, they can lead to very drastic management actions, like removing most of the wood along a river, usually without considering the impact, and they also create this generalized negative perception of wood. So the perception of wood in rivers has been shown in several studies since already 20 years ago. And there has been a set of questionnaires based on pictures like those in the slide. And a few years ago, we did this survey in Spain. So we show people, so not only academics or practitioners, but also people living in different regions in Spain. We show we show them these pictures, and we ask them to rate the pictures um, according to aesthetics, danger, and need for improvement. And there were in total 20 pictures, 10 with wood, 10 without wood. And in general, all the pictures with wood were rated as less aesthetically pleasant, more dangerous, and with a need for improvement. And when we asked what type of danger they expected, they all, or most of them, reported flooding, and also what type of improvement they would consider. In most cases, they answered channel cleaning. By cleaning, they meant removing wood. And this contrasts quite a lot with the results of the questionnaire, and this is also interesting. While most of the respondents strongly disagree with the statement that rivers with wood are less aesthetically pleasant than rivers without wood, there was less consensus about rivers with wood being more dangerous, but it was again unanimous the perception that removing wood from rivers mitigates flood hazards. So we need to understand what are the hazards related to wood and quantify them when possible. So the consequences of the deposition of wood at bridges are the reduction of the channel cross-sectional area, the backwater, and in some cases, the flooding of the nearby areas. So this is an example from Spain where this bridge was blocked with wood, causing a backwater of 2 meters. And this, of course, is the difference. This is another example from Poland, but this shows a similar case. So this bridge being blocked, causing the flooding of the town nearby. And again, here it's important to identify what are the factors controlling a bridge clogging or blockage. And so on one hand is the wood, but also the flow conditions, the river morphology, and the bridge geometry. So the probability of blockage usually increases as the size of the wood and the complexity of the wood increases, and also the volume, but also changes according to the bridge dimensions. So the geometry and span, the presence of piers and the shape of the piers, and the deck or freeboard. So as the only artificial element in rivers, here we should focus on the bridges and not that much on the wood. So this is what we did in this work. So we compiled variables that are easily accessible in any river, and using a database from bridges in the UK, we trained a decision tree that is able to identify bridges that might be able or might be prone to trapping wood and bridges that might be less likely to trapping wood. And so the algorithm that was trained in the UK showed a performance of 60%, but we did a test also with this algorithm in Spain and showed a higher performance, and the combination of the two showed up to 80%. So 80% of the bridges that actually had problems with wood were identified by the algorithm. And currently we are training a more complex model, a random forest, with a much larger database. So once the critical bridges are identified, then the next step would be evaluate and make a cost-benefit analysis comparing different strategies. But this is very rarely done. And actually, this is the only, or at least one of the few studies that exist, comes from the US. And here they compared 3 different management scenarios. So one in which wood is being removed periodically from the river to avoid a bridge to get blocked. Another scenario in which wood is not removed, but the wood that arrives to the bridge is removed and the infrastructure is maintained. And then the third scenario, the third strategy was to leave the wood in the river and modify and adapt the structure, the bridge, to allow the wood to pass. And then they quantified different aspects in economical terms. And what they saw is that this third strategy was actually the best. And also not only in absolute numbers, but also they made some estimates through time, and this strategy was also the most sustainable in the long term. So with this in mind, there are a few guidelines that exist to define management strategies, and here I added a couple of examples, one from the US and one from Chile, but I'm not going into details. You will get the PDF and you have all the links in there, or you can ask me afterwards. So the US recently published a manual with a set of checklists and tools. And we don't have something like this in Switzerland, but we have this BAFU report published after our wood flow project. And in here, we also suggested or proposed some tools and recommendations, but focused on hazards. So still in some cases, different structural measures are required, like for example, these retention racks or structures that are quite common in the Alps. But they must be designed very carefully because they may also trigger unexpected side effects, like in this example. So efficiency of the trapping structure. So the structure was well designed. It trapped most of the wood, but then caused a significant lateral erosion. Then if these structures are not an option, the bridges can be adapted and modified. And there are also different ways to do that. But just to finish, we wanted also to identify the still existing challenges and barriers. And a couple of years ago, we had a project that focused on this, and we organized a set of workshops bringing together practitioners and scientists discussing these different barriers and challenges. And one of the things that was nice to see is that the answers to the questions about the 3 words to define, to describe wood in rivers and the limitations were quite similar from those who responded to the questionnaire. So wood is related to biodiversity and habitat, but also with blockades, infrastructure, and flooding. And out of these 3 workshops that we organized in different countries, here I listed the main remaining challenges that were identified, and I would like to discuss this also with you today, because there might be specific challenges in Switzerland or different ones. But in general, these are the most relevant. So limited awareness of the potential benefits of wood, the lack of understanding of the wood regime, lack of good technical guidance on how to include large wood, lack of monitoring, lack of a sound and robust evaluation. Communication was also raised as an important aspect. Inappropriate location or design when referring to structures. Lack of suitable wood. Site constraints in terms of, for example, the presence of vulnerable infrastructures. And then, of course, uncertainties associated to wood, which are more challenging to quantify or predict than for more traditional structures. So I would be happy to discuss the challenges and barriers that you face here in Switzerland when working with wood in rivers. And with this, I took a bit longer, but I thank you for your attention and will be happy to answer questions.